morning, everybody. My name is Dr. John Gow, and I'd like to present this morning an initiative that we took as part of our mitigations against COVID-19 in respect of engineering programs as we delivered them at the university. And basically what I'd like to do is to take you on a little journey to the genesis of where this idea came from. But before I do that, I'd just like to explain, for the benefit of those of you who may not be engineers or may not be familiar with the concept of what engineers actually do and what we are, I'd just like to let you know a little bit more about engineering as a discipline and what it really actually entails. Probably most of you will be aware that we don't fix washing machines and we don't repair cars. That is really the role of an engineering technician, not an engineer. Although some do call themselves engineers, we are subject to the fact that engineering is not a protected term in the UK, which means that we don't have the ability to restrict the use of that term to those who are actually qualified engineers. But what we do is be creative. Engineering is a very creative discipline, without any doubt. It's about design. We are designing items, widgets, gadgets, from that to structures to large engineering works, civil engineering works that you can easily see around you. And without engineering, the world as we know it would be a very different place. We provide novel and innovative solutions to complex problems. We help the blind to see, the deaf to hear, and the lame to walk. In fact, one of my colleagues works on using reusable products and recycling them to form prostheses. And that is on top of computing, transport, manufacturing, prototyping, structures. The list goes on. Anything you find in your kitchen with a display on it, your toaster, your kettle, your cell phone, your landline phone, if you still have one, all of those have been designed and developed primarily by engineers. So this is what we actually do. We are essentially creating the future. And in doing so, we're looking after the resources that we have. So we deliver these courses for engineering. And one thing that we noticed is that a lot of students coming in to universities into the first year don't quite have the same perception of how engineering has influenced their own lives as we did in our generation. So thinking about this, I'd just like to set the wayback machine to 1985, and in fact even earlier, and introduce you to this, especially that lovely little device at the bottom. You will almost certainly recognize this if you have anything to do with vintage computing. This is an 8-bit computer that I built when I was 13 years old. And I even go misty-eyed when I look at it now. It came out of my attic, but it's still fully functional. It still works, still does what it says it did. And I built this from a kit. Not the way that you build PCs these days by plugging in modules, but each one of these integrated circuits, with each one, these larger ones had 40 pins, and each one of them had to be soldered by hand to the printed circuit board. It then had to be tested. The power supply had to be built from scratch, from components. The sense you get of achievement when you see it work is second to none. I did this long before I went to university, and in doing so, I learned a fantastic amount about embedded systems, about computing, purely through getting this to do things that otherwise would have been impossible with the technology of the time, because it was either too expensive or it was unavailable. Even preceding this, the idea of creating radios over the kitchen sink, many engineers of my generation started out by doing just that. Long before we even attempted a formal course in engineering, we sat there and built things. It was something that we were driven to do this. If you wanted something, you couldn't afford to pay for a ready-built unit, so you'd build it, you'd design it and build it yourself, or you'd build it from a kit initially. And then you'd tweak things, you'd change things, you'd constantly be asking yourself, what if I do this, what if I change it? And you would change things and you would see what worked and what didn't in a very practical context. So you could extend these. This was fantastically extendable, and you can see there a little add-on board that I put together containing some additional circuitry, which allowed this computer to do just that bit more than it could originally. And although it's not displayed in the photograph, this was connected to a monitor. It pretty much could do most of what even a modern computer could do, although perhaps not as pretty. But the power of what it could give you in terms of the joy of seeing things that you have created come to fruition is basically second to none. Now, where this is going is simply because when we look at the genesis of an engineer, how people become engineers, if we look at the pre-1990s, the technology was available. But if ready-made devices were available, they were often outside of budgets. You couldn't necessarily buy the gadgets that we can today. So if you wanted them, you had to build them. And to do that meant you had to acquire hands-on skills. And that was a driver. We actually had to build things, to put some effort in to see the rewards. And the rewards were that we had something that very few people had that was probably, if you bought one, would cost considerably more. But people built radio sets over the kitchen sink. That's a common phrase that's often bandied around by people of my generation. But in reality, that's actually what happened. Generally speaking, it was a lot more than just radio sets. Computers had to be built from components. You couldn't just walk into Currys and buy one. The average cost, inflation adjusted, would be several £1,000s, much more so than the value of the same technology today, which is considerably more capable. And these had to be built from components, not modules. So in this, we developed a passion, a real passion for understanding what you could do with the technology. And in doing that, we also learned the theory. No formal training, but this came along with the territory. Once you started to understand what works and what doesn't, you start to see how to make things work. And you start to ask yourself more questions. Where ready-built computers were available, which they were in the 1980s, some were, it was very common for people to build add-on units. So even with the ready-built technology, to make it do something more useful, you would also be able to build add-on something that you had created. So this concept of creativity was built into the DNA of engineers in our generation right from the ground up. And it required the development of fundamental electronics knowledge. In the mechanical world, cars much more accessible from the point of view of repair. And many of us bought cheap cars, kept them running because you could. And you developed a huge skill set in the process. The point is, this whole process has captured the interest of people. In general, quite a large number of people. It crosses class boundaries, it crosses gender boundaries, it crosses every kind of boundary, but it develops the passion of creativity, and without passion, there's no design. So let's fast forward to what we see today. There's an abundance of gadgets at low cost. Schools don't encourage engineering style design as much as they perhaps used to. Design has tended to move more towards the, for want of a better way, prettification of an existing gadget rather than the design and the creation of the technology that actually makes it work the way it does. Cost, time, and expertise is the driver that's prevented this from being developed further within schools. And crucially, most of the students entering university, having talked to many students, have never experienced this. They've never sat down with components and actually built something and seen the sheer pleasure of the flashing LEDs under their control, without somebody telling them they have to do it or somebody giving them step-by-step recipes, but to actually drive it themselves and create something new. This has somewhere been lost. And this was very much a case that it was something that I was thinking about for many years. As an engineer, I could not understand where the passion had gone. And a lot of fundamental learning outcomes in engineering now have to be delivered from ground zero without this starting point. And as such, the connection between creativity and engineering design has been lost. Largely at a very early level, and before they even get to an engineering program. Some regain it, but it takes a lot more time. So one of my thoughts was, how do we deal with this problem? And one thing that worked particularly well for us, although unfortunately it wasn't a particularly good experience generally, was COVID-19. Hitherto, we taught laboratories this is a typical example of some of the equipment that would be used in an electronics engineering laboratory. There's nothing particularly unusual about these. It's a standard setup. And we had students coming in who had never even seen the concept before, let alone used the equipment. Most of us in my generation had seen it, even if we hadn't actually used it, and knew of this equipment. And we're having students in the first year that the concepts are missing, and so is the experience of actually interacting with basic equipment used to test and design, the sort of thing that we would have developed as we went along as individuals on our journey before we even got to university. So how do we correct this? Without delving into the school system and making radical changes there, it seems that something has been lost in society. How do we put this back? And so COVID-19 came on the scene. National restrictions led to the closure of our facilities. Our laboratories were shut. This was a turning point in the way we could deal with this problem, because the need for students to be able to design and develop these solutions, the learning outcomes, as we call them, didn't go away. We still need students to be able to be practically capable as engineers, and engineering is a vocational and practical discipline, as I've said before. So, whilst our solution to this was to appeal once again to the natural curiosity, the natural passion, the natural desire to create something and provide home lab kits, which is essentially a lab in a box. We created a system whereby students had access to the test equipment that you've seen in the previous page, but in a fashion where it was relatively cheap, easy to obtain, and we could mass produce this or mass distribute it amongst students. The idea being then they could take this away in conjunction with some instructional videos, one of which we'll see in just a moment, and this would enable the students to work at their own pace, using their own equipment in the space of their own home over the kitchen sink, see the projects develop, see the solutions, but best of all, and one of the most important things, it gave them permission to experiment. So we developed two sets of kits, one for electronics disciplines, electronics test equipment, we'll see the examples of those in the next slide and in the video, and one for mechanical disciplines that hopefully my colleague will be joining us shortly from mechanical engineering, and I'm hoping that he will be able to describe a little more on the mechanical side. As I say, I'm an electronics engineer, that's my background. He would be he will hopefully be able to provide much more of a comment on the mechanical side. So with those in mind, the electronics kits consisted of a complete lab in a box, in a bag actually. We did waive the 5p bag charge even. But these will allow the students to perform their curricular work in the comfort of their own home, give them permission to explore, to make changes, to see what happens when you change something. And also, with us online, with us available, to actually ask questions. So if something happened that worked differently and they weren't expecting it, to ask a question and find out why. And that opens up a whole avenue for teaching and delivering the core theory behind the practical work. It gives the students the ability to design. We even put an Arduino in there, so embedded systems was a possibility. They could design microprocessor systems, again, in the comfort of their own home. And these platforms that are now available have actually, despite the fact that they've made it easier for people to experiment in their own homes, it's sad that fewer individuals have actually attempted this before they go to university. Arduino is a cheap platform, and it brings computing, the type of computing we did in the 1980s, within reach of anybody, and it's a fantastic environment to work with. But not that many have actually experimented with this, despite the option being there. And I wouldn't like to speculate on the reasons, but the ubiquity of technology is perhaps one of them. It's all too easy to pick out a phone and play on something that's an app that's been provided, without actually going to the effort of thinking, well, I want the app to do something different. How do I do this? How do I write my own? And then how do I get this to control something? And then you're in the realms of electronics engineering straight away. And there's a lot of scope there. The mechanical kits were a little bit more involved. They were targeting more for the first year. But this is just an example of some of the equipment that we gave them in the lab. Not the whole kit by a long stretch. One of the really useful pieces was this little oscilloscope. When once upon a time in the 1980s, you'd be looking at a minimum of several £100 for even a basic model oscilloscope. These little things are only £20, £30. And you can get them very easily in volume. And they work fantastically well as a base level entry example. They're cheaper, they're simpler, but they work in the same way, and they provide access to the same concepts that would be used in a full-size lab. So with that in mind, what I'd like you to see is this little video. It's about 15 minutes long, but it's the introductory video that we gave. We created a set of videos for the students, including this first introduction to the home lab kits, and then a whole series of videos with instructional details on how you could use these effectively within your own home. So yes, let's have a look at the video. And then I'll explain a little more about how this impacted on the students' performance and how it was received by the students. Welcome all. If you're joining us at DMU for the first time, hopefully by now you've had a chance to meet some of us, even if only virtually. And to those of you who have come back to us for your second and third years of study, well done, and we're looking forward to a new year together. Now hopefully by now you've heard something about our home labs, or sometimes referred to as a lab in a box, even if it is just a whispering in the corridor. Or maybe you've been to one of our open days or browsed the DMU website. This short video is the first of a series introducing you to this new concept for 2020. It will focus on introducing you to the home lab kits, their contents and some basic guidelines for their use. Further videos in the series will provide you with more details and guidance as to how to use the individual items within the kit. Now I'm talking to you today from my own home lab. Designing and building electronic circuits is a lot of fun, and as an electronics engineer of 28 years odd experience, I have over the years developed a fully equipped home lab that makes this experience so much easier. We are providing you with a set of equipment that, while simpler and less fully featured than those in the lab, will enable you to do almost exactly the same things, and certainly it will enable you to complete your coursework at home should you wish to do so. It will also enable you to go beyond the curriculum. As you develop your skills and feel confident in doing so, why not try building kits, for example? They're easily available online, and there's a large number of different gadgets you could build, or useful pieces of equipment. You could even build test equipment to extend your home lab. Of course, you will need the home lab itself to help you build that and debug it. So, here's one I prepared earlier. Your DMU home lab will come in a rather anonymous looking carrier bag. We've even waived the 5p bag charge. Your program leaders will provide you with information as to how to collect them. Unfortunately, you will need to come onto campus to do so. They're too large and heavy to post out. But in the meantime, let's have a look at the contents and how the home lab is structured. Our home labs are divided into two main parts. Firstly, in the bags that I've just shown you, you will find your core kit. This consists of a comprehensive toolkit together with a set of basic test equipment that will allow you to take measurements of various electrical parameters. These parts will be described later, and more detailed instructions on each of the parts of the core kit will follow in successive videos in the series. But for now, please be careful with the kits. They are relatively fragile and can be easily damaged by crushing or by abrasion. I would recommend you obtain a small rigid plastic box, perhaps with the compartments in which to keep these small parts in the kit. Now that covers the core kit, but each of your modules is going to be different. It will cover different parts of the electronics discipline, it will meet different learning outcomes, and you'll be building different circuits and performing different experiments within each of them. And therefore, separate to the core kit will be a series of module packs. So in addition to the core kit, you will be given module packs for each of the modules. If you're in the first year, the module packs will cover the following modules, which will be Electrical and Electronic Principles 1 and 2, Electronic Circuits and Systems, and Principles of Design and Manufacture. There may not be one kit per module, but one kit may cover more than one module. If you're in any doubt as to what the module packs are required, please consult the module leader for the relevant module. In the second year, you have 3 heavily practical modules, and it's here where the core kits and the component packs will really benefit you. So in year 2, you will have the following modules, which will have module packs: Applied Electronics, Embedded Systems Fundamentals, and Embedded Design for Internet of Things. These are the modules that will probably make the most use of the lab in a box. But please don't feel that's exclusive. You can of course use this kit to cover any material at any point in the course, and when you reach your final year project stage, more than likely you'll be using the kits even then as you debug and develop hardware for your final year projects. And of course you really will want to do a hardware project, hopefully. So let's take a look at some pictures of the kit and see visually as to what this kit actually contains, and I'll give you a short description of what you'll actually be looking at as you unpack the kit. One of the most prominent and useful features of the home lab kits is the toolkit. This comes in a zippable bag and contains almost all of the tools you'll need to perform most of the practical tasks in electronics. Along with an assortment of screwdrivers, the kit also contains a pair of pliers, a pair of side cutters which are useful for preparing and stripping wire, a one-click automatic wire stripper, a set of Allen keys, an integrated circuit extractor for removing integrated circuits from breadboard. It can be sometimes quite difficult to do with your fingers, and a multimeter along with a useful pair of tweezers. In addition, the kit contains a soldering iron, solder and a solder sucker. Please view the video on soldering technique and how to safely use a soldering iron before you use this. It will save damage to surfaces, burned fingers, a lot of swearing if you know how to use them correctly. And there will be plenty of instruction available on how to solder. It is a technique that takes time and skill to master, and it is a very useful skill to have in electronics, as you can imagine. Here's a close-up of the multimeter, which is probably one of the most common and very useful pieces of test equipment in electronics. It will need a battery. You will have to provide the battery, unfortunately. They don't come with the multimeter, but they're standard batteries that you can buy in any shop, and a later video will show you how to fit them and how to use the multimeters. They're so called as multimeters because they can measure multiple electrical and electronic parameters. In this case, it can measure DC voltage, AC voltage, DC current. It can measure the gain of a transistor, test a diode, or measure resistance. The downside is it can only measure one parameter at once. That means we provide a second multimeter to enable you to measure more than one parameter at any given time. Don't lose this little guy. It's a plug which enables the multimeter in the toolkit to measure the gain of a transistor. If you lose the plug, that functionality will be lost. It'll be very difficult to get another plug as well because they come with the toolkits and the multimeters. You probably have to buy another toolkit if you desperately wanted to get that plug again. It's not secure in the bag, so please just take care that you've always got it in there. Here's the second multimeter, and as you can see, it measures much the same thing. Voltage, AC voltage, DC current, gain of a transistor. This doesn't need a little plug because it has the plug integrated into the multimeter, which is the part used for measuring transistor gains. It can test diodes, continuity testing, and measure resistances. The resistance measurement can be quite useful if you pick up a resistor and you're not sure of its value. And this is something that you'll learn as part of your studies here. A later video will show how to use these multimeters and how to get the best out of them, as well as how to fit the battery. This is an oscilloscope. It allows the graphical display of voltages that vary with time, and it's an essential tool when developing anything that manipulates signals, for example, sound. The tool doesn't need a separate battery, but it can be charged up via a USB port from any charger or computer using the cable supplied. The USB cable isn't shown in this picture. There's a little socket at the bottom there that it plugs into, and you can charge it up using any charger or any computer. It's a single channel oscilloscope, meaning it can only display one waveform at a time, and it does have limited bandwidth, but it will be more than adequate for completing most of your coursework and most of the experimentation that you'll do as part of that into your project and even beyond. It's a very useful tool, even if in the future at some point you do decide to buy yourself a full-size oscilloscope. This can be very handy to have. The next is power supplies. You get two of them because more than often we have to generate more than one power supply. We need two voltages of different levels when developing and testing electronic equipment. So we provide you with two. These take standard mains and convert it via an isolated power converter to lower voltages, somewhere between 3 and 12 volts. That can be adjusted via this knob, and the voltage at the output here is displayed on the screen on the 7-segment display here. When you're using it, always test the output with a multimeter, because so often these aren't particularly accurate, and so the voltage might be off by a volt or two. And it always pays to check using a piece of test equipment that your power supply is giving you what you expect. Always treat power supplies with respect. Don't expose them to any liquids. Certainly don't get them wet. If you do, consider them to be unusable. If there's any damage to the plug, to the mains cable, or even to the output cable, or if there's any damage or any kinking or any nicks in the cable, in the insulation, again consider them unusable. Always treat power supplies with respect. Don't forget you've got mains coming in at one end, and this is quite safe providing the cable and the plug is intact. If there's any damage to the case, if it's cracked, again it's time to get another one. So please always treat these devices with respect. This little board allows you to connect the power supplies to a breadboard in many different combinations. It also contains a useful circuit to provide a variable voltage from 0 to a maximum of the applied supply. You can connect the two power supplies shown on the previous slide to these ports here and here, and on the pin headers you'll be able to get a voltage out which is up to and equal the sum of the two input voltages. And given that you can control the voltages on the two power supplies independently, you can get quite a wide range of different voltages. You can also reconfigure this to give you two independent voltages, one from each of the power supplies, and in that mode it's simply an adapter between the plugs on the power supply and the pin headers that you'll need to interface with your breadboard. The little variable voltage source is affected by this preset pot here and the small op-amp, which provides a buffering circuit. And on this jumper here you can pull off a voltage which can be set fairly accurately by turning this between 0 and the maximum applied voltage. Now obviously there's no display on the board, so you'll need to use a multimeter to measure that voltage to ensure that you can set it accurately and that the voltage you're getting out is what you expect. But it has a lot of uses as part of the test regime when you're testing a piece of equipment that you've designed. This is the signal generator. It can provide alternating voltages at variable frequencies, and you can achieve the adjustment by changing the relative position of these variable resistors here, and you can change the wave shape by changing these headers, and you can get a sinusoidal wave, a triangular wave, or a square wave out of this at varying different amplitudes and offsets. However, there is no display on the board, so once again you'll need to use this in conjunction with your oscilloscope and your multimeter possibly to get the best out of this and to set the output accurately. You'll also need to provide a power supply from the little power module on the previous slide. Instruction will be provided in a later video as to how to get the best out of this piece of equipment. This is your breadboard. It comes in a box with some jumper leads and a little module that helps with the provision of regulated supply voltages for some projects. Most of your prototyping and design will make use of these breadboards, so do take care of them. Now, we do know that you've got several modules running in parallel, and any modules that require a breadboard that are running in parallel, we'll make sure you get an additional breadboard in the component packs for the module to ensure that you don't feel that you have to use just the one breadboard for two modules running in parallel. And that means you don't have to walk into a session, do some work, and then feel you have to rip it all out to put in the components for the next session. You'll be able to get a second breadboard which will enable you to complete the work on one breadboard without having to reuse that at the same time for another project. Jumper leads, they're quite useful. They enable you to make interconnections on the breadboard quite easily, but as you'll see as you go through the program, their length can be something of a disadvantage. As you study electromagnetics, you'll realise that they also make good aerials and can pick up noise.
And so some of these factors are just useful little bits of information that you'll start to understand as you study the science of electronic engineering. The little power module is quite useful because it can provide a 5 volt and a 3.3 volt supply to projects on the breadboard, not only from just one of your power supplies, but also if you have one handy from a USB port, which will give you either 5 or 3.3 volts, not variable, you get one or the other. And you can supply that from either any USB port on a computer or alternatively a charger, a standard phone charger. And you can use that with certain projects, but not all. Here's the breadboard out of its box, and you can see here that it looks a little bit smaller than it is inside the box. But again, you'll get more than one, and in fact in the second year projects you'll probably find you need 2 or 3. Certainly for applied electronics you'll need 2, I would have thought, at least. And then the embedded systems modules, again, you'll need more than one. But those breadboards will appear in the component packs and not necessarily in the core kit. You can never have enough jumpers, so we provide you with a few more. Clearly the power supply combiner module and the signal generator require a connection to pin headers, and these leads provide that. So you can plug these female connectors into the pin headers and then attach them to your breadboard so that you can connect test equipment easily to and from your project on the breadboard. And finally, if you're in the first year, you'll get an Arduino in your core kit. This is a traditional Arduino Uno, but think of it not as an Arduino, but think of it as a microprocessor development board. You'll learn to use this in ways that are much more demanding than traditional Arduino projects. And make no mistake, the language you'll be writing the firmware in for this is C++, industrial standard C++, and you will also be learning how to interface this directly to some very complex analog and digital systems. Remember, it's an analog world, like it or not, and you have to be able to understand an analog world in order to be able to convert that to a digital signal for processing in what is essentially a digital computer. And so essentially some of the modules at least, will focus on interfacing, whereas others will focus on programming. But embedded systems are a major part of electronics design as it stands at the moment, and it's hard to think of any appliance that you might even find in your house that doesn't have a microprocessor in it. So microprocessor engineering, which is essentially what this is about, is a core part of the program, and this will give you your own kit where you can experiment both as part of the curriculum and on your own in this key area. Now there are a few items for which I haven't got slides. In your core kit will also come a small stock of various components. That will be resistors, capacitors and some integrated circuits. If you don't know what these are because you've limited electronic experience at this time, please just keep them safe. Their purpose will become known as you go through the program, but please don't lose them because they are costly to replace. Also, hookup wire. I did mention quite deliberately that some of those jumper cables, though very useful in initial prototyping, do come with disadvantages. And with hookup wire, which is just simply nothing more than solid core wire, you can use the tools in your toolkit to make very short point-to-point lengths, which are much shorter than the jumper wires. They make for a neater layout on the breadboard, and above all, shorter connections point-to-point, which is something that you should be aiming for in nearly all designs. So there's an overview of the core kit. The module packs will not be part of this video series, but they will be explained or more information will be provided as part of the modules themselves. And that's it for now. The next one in the series will cover the multimeter, how to set it up and how to use it to take measurements of basic electrical and electronics parameters. Just one more thing to mention. The kits and the toolkits are yours to keep. However, if you lose or break anything, you'll need to replace them at your own expense. Our technicians can help if you need to know where to go about purchasing replacements should you need them. And safety is largely common sense. If you're in any doubt about how to use anything, please ask us. Providing the kit isn't abused, there should be no dangerous voltages present with which you could come into contact, but you could damage parts of the kit if you do not pay attention to correct power supply voltages and connection polarities. Have fun.
Oh, there's absolutely nothing worse than hearing yourself. Actually, there is. There's hearing yourself and then having to watch yourself as well. But that's basically an introduction to the electronic home lab kits that we produced and provided for the students. This was one of a series of 6 videos, which went into some of the detail of how individual components and each individual parts of the kit were used, and it concluded with an exhortation on the part of us to the students to essentially say, experiment, feel free to experiment. This is a learning exercise. If you go above and beyond the expectations of the curriculum and just see what you can actually do with this stuff in the comfort of your own home with nobody looking over your shoulder. We've turned on its head the whole concept that some universities seem to have going back to even a few years ago, where laboratory equipment was hidden behind glass cases and was very difficult to extract except for scheduled sessions. This is all about bringing practical work within the easy direct reach of students, and being able for the students to learn by exploration and to once again develop that passion for creation that is key to a successful engineering or a successful career in engineering. I'd like to introduce my colleague Ian. He's joining us now. We'll talk a little bit about the home lab kits that we offered for mechanical engineers, which clearly always will differ from the electronic engineers, and and you'll see they will look different. As you would expect, and focus more on some of the learning outcomes for mechanical engineers. I think he's got some nice little demonstrations to show, and these will show how the mechanical engineers would interact with this, and also how we plan to take that forward. And following that, there'll be an opportunity for any questions and answers relating to the home lab kits. We'll wrap up after Ian's short session. So over to Ian.
Thanks, John. And I'm sorry you can't see me. I may be able to just wave because I've focused the camera on my table so that you can see things. I do have a glamorous assistant with me as well, Anna, who's because I needed an extra finger. So I thought what I would do, and they're slightly different from the electronics kits in the sense that the electronics kits they were using in multiple things throughout the term, whereas the mechanical ones tended to be things that they used particularly to show concepts, but also to do some calculations on. We actually found them very useful, and to the extent that we've carried them on this year. We used our subject group budget to purchase what we had before and expand them. So one of the things you can see here was actually developed by Anna, who is sitting to my right but doesn't want to say hello, which is something that she's developed actually for year 0. And I'm also going to show you some things that we've got in the pipeline that we're planning for. We haven't used with students yet, but we are preparing to use with students. So after that, I might just move the camera around so you can see me as well. So let me start off with, in a sense, the crux of what we started with, because it affects a number of the other things as to how they perform. And that is, this is why I need Anna. So this is actually the one item that we had to partially make ourselves. So we bought lots of fidget spinners, which was it 5 years ago? They were very much in vogue. They're no longer so much in vogue, but nevertheless, they are a very interesting device. They are, in a sense, a gyroscope. And the reason that people found them interesting is when they were spinning them and they moved their hands around, they felt a sort of odd feeling as it was resisting that rotation. And that comes about because of a thing called precession. So what we did in order to show that, and this is actually my prototype rather than one of the ones that Stephen made a lot more neatly than these ones. And if I just take it off your finger for a second, what we did is we took the fidget spinner and we attached a wire to it. So there is a little hook, which is just a picture sort of hook that goes on the back of a picture for putting wire on it. And I'm not a fisherman, but you can see just about in the middle there what is, I'm told, and if any people are fishermen, then I'm really sorry if I've got this wrong, but I believe they call them a swivel. Essentially, what it does is it allows this thing to rotate around like that. Now, there's a reason I want to do that, and this is why I'll take Anna. The first thing to note is that when you've got something like a heavy device like this, which has got a hook on one side, it's top heavy, so if I let it go, it will start oscillating, but it will tilt over and lie flat so that its center of mass is pointing directly through that wire. But, and this is really important, and it's the big difference that you get when you go from school to university studying engineering, is that things suddenly become 3D. And actually, the fact this is three-dimensional really matters. And so if I give this a spin like this, you can see two things are happening. First of all, it didn't initially. It took a while before it toppled over. So I'll do that again. And it's staying upright, but and the reason we put the swivel on it is it's rotating around. And actually, the way it rotates depends on the direction of the spin. So if I spin it in the opposite direction, you'll notice it's spinning in the opposite direction. This is a classical gyroscope. Traditionally, you'd use a bicycle wheel, and a bit difficult to get students to have bicycle wheels. So we gave these out, and we're doing the same again this year. That gets them to the idea of precession and gyroscopic stability. And without going too deeply into it, essentially what's happening here is that when it's toppling over, it topples over because we get a moment. So, and that moment is about an axis in the way I'm pointing, which is directly towards Anna. But I'm spinning it about an axis. So if I hold it like that, then I'm spinning it about an axis perpendicular to this device. But just think about what happens if it's spinning around like that. Then as it topples over, it's now spinning around like that, about a third axis. So it's toppling about an axis towards Anna. It's rotating initially about an axis perpendicular to the device. And if it's toppling over, then its rotation is about a third axis, but crucially an axis in which there was no moment applied. So when I applied a moment to get it spinning, I applied a moment about that axis, but when it toppled over, it didn't have any of that, any moment about that axis. Newton actually said that's impossible. And so it responds by rotating around in the opposite direction. So if you hold it up again, so you can see that it's rotating, a little bit too vigorous there, whoops. It's rotating around in the opposite direction. And of course, when I spin it the opposite way, again, it compensates so that there's no net moment about it. Now, that is a very common thing, and it's really important for mechanical engineering and indeed for aeronautical engineering because of the prevalence of rotating devices, whether that's turbo machinery, washing machines, car, tires, etc. But there are actually some other things you can do with that. So, and I brought a few of them along here, and these were part of our kit. And I must say that we had a few more things in our kits as well. So the first one I've got is a little spinning top. And that spinning top, we're all used to the idea of spinning tops and they can just spin around. But the interesting thing about this spinning top is it's got a sort of sphere at the bottom, and the center of curvature of that sphere is higher than the center of the mass, which is towards the bottom. If you think about the directions of the moments that creates if it starts to topple over, then the whole thing becomes unstable. And what should happen, hopefully, and I put it on a plate to try and keep it in one place. A bit faster. I'll get there in a sec. There you go. Is it flips over and spins about its thin point. That is a more complicated, but it's just behaving via precession. And of course, we've got the students to think about how that was possible. And I have to say that there's a famous picture of Pauli who absolutely could not explain that, and yet it's just precession. And in fact, sorry to embarrass John, but there's a famous Christmas lecture by an electrical engineer about gyroscopes, in which he was claiming that Newton's laws didn't apply, and actually they behave this way precisely because Newton's laws do apply. Chap called Professor Lathwaite. He knew lots about electric linear motors. He didn't know anything about gyroscopes, as it happened. The second one I was going to show you, which is also part of our kit, is a thing called a rattleback. And these were actually discovered by accident a few thousand years ago, when they were called celts, spelt like the word Celts, which is actually the Greek word for, it doesn't make any sense. And the reason it doesn't seem to make any sense is that what happens with this depends very much on the direction that you rotate it. So if I rotate it one way, it just rotates around, although it is doing something that we might want to discuss. But if I rotate it the other way, oops, put it on the table, it jumps up and down, and you'll notice it changes direction. That is also an example of precession. So what we're seeing here, as it rotates, if it rotates in one direction, it creates precession, which stabilizes its vibration about one axis and destabilizes it about the other axis. So we've got two axes here. We've got an axis through the middle and an axis through the middle across it, and it can rotate, it can oscillate about either of those axes. If I rotate it what was anti-clockwise forward, then it actually stabilizes the rotation about that one through gyroscopic precession, but it destabilizes about that rocking motion. So if I spin that again, you may notice that actually, although it does continue going in that direction, it is rocking from side to side as it slows down. Whereas spinning it the other direction, it jumps up and down. So that's just a sort of flavor of what we did. I'll just show you one more thing just to show it wasn't just about gyroscopic things, which was a tornado tube. And what we have here is just two bottles. I think these were Voss. Is that a mate? I think it's Voss. And they're just convenient because they're a nice shape. And this is just a connector that joins the two bottles. So it replaces the cap and you join them together. And I put water in the bottom bottle. And I don't know if you can see it, but there is a big hole down the middle. A bit difficult to see over my shoulder. But if I turn it upside down, then the first thing we note is the water stays in the top bottle. And it does so as a combination of the compression of the air in here and the expansion of the air at the top, not to mention the fact that air pressure is quite big anyway. So then the question is how you might get the water to flow, and you could do that by drilling two holes to even up the pressure, or if you give it a spin, you get another instability which creates a tornado. If I had more time, I would go through the mechanics of what's going on there. We of course got the students to do that and to do some calculations. So that's not all the things we did last year, but it's some of the things we did last year. And the reason I'm not going to show you all of them is actually we've moved forward a bit, and it worked so well that we thought we'll carry this on for some additional things. So this is something that Anna developed, which is a force board, and we have a large force board down in the lab, in the mechanics lab or the materials lab, and the idea is you have well, the main thing is two pulleys, and I've got a weight on one side. I'll try and lift up because it's hanging off the table, and a weight on the other side, and then a weight in the middle. And of course, when I do that, then this has got to be in equilibrium. So the angles here are such that the tensions in these two wires must vertically balance the tension in the wire hanging down, and of course horizontally they've got to balance each other as well. And if I put more weights on it, then I can change that angle. So if I put another weight on it, like that, it moves down, or indeed if I remove some weights, it will move up. Now, Anna being Anna doesn't do things by halves, so you may notice there's also 2 pulleys at the bottom, which actually gives us the opportunity to put more horizontal forces in as well. And you may notice there's an extra wire here to enable us to do that, and we can wrap those around those pulleys. So that's one of the things we did for this year. Finally, I thought I'd look to the future. So there's a couple of things that we've done, and actually there's lots of things I could show you, but I'm just going to pick out a couple of them. One is towards material science, and so what we did is we made this little thing here, which is basically full of ball bearings, and just see how they stack. And what you notice is that, generally speaking, if you look closely at regions, they stack quite neatly, but not everywhere. We get these lines here, and that would correspond in a real material to a dislocation and a grain boundary. So that line would be a grain boundary, and these little spaces here would be dislocations. And that's really important to how things break, and it's why, for example, you may be able to see a fan blade on my desk there. A lot of turbine blades are now being made with single crystals. Time for one more thing, is this one here, and I'll show you a couple of things here. So one is the portable one that we aim for students, which is literally a piece of rubber, and all I've done is I've put a saucepan lid attached to it, and if I lift it up, it resists me. And yet, if I lift it from the corners, it lifts up really easily. And that's because of the air pressure on top, which is converted into a force through the area. So if I make the area bigger, for example, with this one, then now I can't lift it up at all. And in fact, the table was lifted slightly off the floor there in doing so. And yet, as exactly the same, if I lift it underneath to release the pressure release the vacuum underneath, then it lifts off. I believe we're getting very short for time, and John wanted to allow time for questions. So I'll hang on. I'm sure that John I might just move the camera around now so you can see me as well. So, hello.
Okay, thanks, Ian. Thanks for that. So once again, if we look at the outcomes of this, these home lab kits were very popular with students. There was no doubt about that. It was reflected in the feedback we had. We issued first year and second year students with the kits, first year for mechanical as well, but first and second year for the electronics kits. The students are continuing to use them. For those who were issued in the first year, you're using them in the second year. We have second year students who are issued them and now using them as part of their final year project. Many students have actually augmented the kit. They've bought kit that's of a higher standard, more capable, and started developing their own home lab. And of course, we are making some plans to extend these kits, although unfortunately budgetary constraints have prevented them from being used on as a wider scale as we did using the outbreak. So essentially, the whole concept of the lab in a box did work in the way that we intended it to do, and it gave the students the ability primarily to be able to experiment. It gave them permission to ask what if, and more is learned from natural curiosity and from exploring that than often is learned simply from reading books. And so the contribution that these have made goes some way to changing the experience of students from not having that background of experimental work, of informal experimental work before they got to university, and in some way giving them the opportunity to widen the remit and start developing and developing, creating new solutions going forward. And as it seems, this was very much a successful enterprise, was putting these home lab kits together and giving them to students. It did what we set out to do. And it's something that we'd like to see taken forward. It has been noted by professional bodies as being a good practice. It has formed the subject of further studies as to how this could be developed further. So this is just a big thank you for all for listening. I'm hoping you got something out of this. I do apologize for the audio quality during the video presentation. It was a function of the streaming platform that we're using. The original video, of course, didn't have those breakups, but I'm hoping you could still follow that as intended. So we're open for any questions. If there's any questions from the floor, please post them, and we will do what we can to answer them at this stage. Or any comments would be welcome as well, as to how you would feel about the whole process and how lab kits you feel would work, home lab kits, and encouraging home experimentation has gone some way to try and recover those lost experiences that students of our and perhaps later generations don't have. So we're open to questions. Thank you very much for your time.
Nothing coming through. Okay.
Okay, no questions that stands at present. So we'll. I'm just. We're here for anything. It may take a moment to type them. That's absolutely fine. But yes, any comments would be welcome. Any thoughts?
Any ideas for what else we could do, particularly on the mechanical side? We'd love to hear that as well. Practice.
Oh,
comment come in.
What are the best soldering techniques? There's only one simple answer to that. Most of us who solder find our own way to solder. There is the trick really. If there is a trick, is to recognise that you need to get the materials you're trying to join hot enough. Most of the biggest problem that electronics engineers, or the mistakes they make, is just not getting the material hot enough. Feeling then just don't put the iron on the joint long enough to heat the joint up. And it's actually the solder joint you need to get hot enough to the temperature that melts the solder. Otherwise the solder doesn't flow properly. So by far the most common mistake is just not getting the joint hot enough. Modern electronics can withstand the heat of a soldering iron without a problem. We did have an issue back in the 1960s with which was actually before my time, with transistors, early germanium transistors that were very heat sensitive, and as a result they had extremely long wires, and you got all of this worry about cooking semiconductors and destroying them by soldering. But modern devices, not really an issue. So if you want to learn how to solder, the biggest fear to overcome is just not getting the joint hot enough. Another one is not tinning the iron. Make sure the iron is good and clean, and that you have nice shiny surface on the hot part of the iron before you apply it. If you've got any oxide on the surface of the iron, it won't transfer the heat to the joint as effectively, which means you're then pumping in a lot of heat and not necessarily it being transferred into a way that can solder. So get the iron on the joint first, warm up the joint, apply the solder. As you apply the solder will then start to flow, and as soon as you get enough solder flowing in the joint, leave the iron on for a second or more and then remove it. The best technique is practice. It takes a moment to get it right. It's not something you can learn immediately. As an example of that, we had a widening participation event here at DMU where we had a local school send some students in, and we got them building radios in one of the labs. They loved it. It was fantastic. And these were 12, 13-year-olds, and we had them soldering. Some of them actually could solder better than some of our undergraduates by the end of the session. It was quite amazing to watch. And it really is, it's not a difficult process. It's just you have to understand the mechanics of what's actually happening. There's as much about material science and soldering as there is about soldering, but the practice of it is just practice. The more you do it, the better you'll get at it. Hopefully that answers the question. Anything else? Is there any more questions or comments? Okay, well, in the absence of any comments or questions, thank you for your time. I hope this was informative. I'm hoping in some ways that those of you who aren't from the engineering profession have a clearer picture of what we actually do as engineers, and how this will benefit students' learning in general. So yeah, I hope you enjoyed the demonstration, and Thanks for your time.
Thank you.